And one of the most famous topics of statistics and probability is the normal distribution, which makes a beautiful bell curve. So when you have continuous data, so binomial distribution looked at discrete data, a certain number of trials. When you have continuous data clustered around a certain value, so the value right in the middle here, it forms a symmetrical bell curve. This point right in the middle happens to be our mean. And if it's symmetrical like this, we call this a normal distribution. And one of the reasons it's connected to the binomial distributions is because if you do enough trials with a binomial distribution, the histogram starts to look like a bell curve. So you know we had, right now we have in our calculator and in our stat list the multiple choice test where you guessed. 0 to 20 questions, you guessed what? 1 out of 4 chance of getting it right. If I draw a histogram for this, so I'm going to go stat plot, number 1, turn it on, histogram, list 1, list 2, make sure I'm going to clear out everything else I have in Y. Zoom 9 for statistics, not a good window. We went from 0 to 20, X scale by 1. What was the highest percentage chance? 20%? I think it was for getting 5 right. So I'm going to just put a maximum at 0.25. Now when I graph this, notice this section. Does it start to look like a bell curve? Not quite, but very close. And if you had a multiple choice test of 1,000 questions, it would become even closer to a bell curve. So that's the connection between probability distributions and normal distributions. Now, normal distributions are for looking at statistics that has continuous data. How tall are people, right? Would you say that there's an average height, right? And there are some people that are really tall, but it's not very many of them. And then as you get closer to the average, there's more and more people, and then, you know, there's some people that are really short, but there's not very many of them either. It's not if... So our height curve matches the bell curve. If you had a height curve like this, okay, that's not very likely. But it could happen if we decided to take a classroom and say, this is going to be a mixed classroom. We're going to put kindergartens and grade 12s together. Then I could get that curve. Do you see that? Because this is the average kindergarten height. And then there's some tall kindergarten kids, right? They're like, ooh. The tall kindergarten kid does not even come close with the short grade 12. So there's almost nobody in this sort of heights in between, but then the grade 12s come up again. So we can make curves have different things. But if you looked at average height of adults in Canada, it would form a curve like this. And so businesses need this information because if you have a fashion store that you're designing clothes for, you're not going to order the same amount of extra smalls, mediums, large, extra larges, double XLs, triple XLs, quadruple XLs. Because there's not going to be very many people coming in for those super, super smalls. There'll be a few, so you need to get a couple, but not a lot. You need to get a lot of the average size. Okay, so notation-wise, we've got 2 parameters. We've got the mean and the variance. Oh, I'm so excited for you guys. This is like a very important topic, and you don't know much about it, but you're going to learn about it. So it's really, really good. Okay. Properties of the normal distribution. So in that bell curve, you always have your average in the middle. They take that middle point and they count 3 standard deviations above and 3 standard deviations below. Once you figure out the standard deviation for a set of data, you can basically say, I know that almost everybody is within 3 standard deviations, right? There might be some 7-foot freaks out there. Well, not freaks, that's not nice. But really tall people that are beyond 3 significant, but they're very unlikely. Not very many of them, okay? And so, one other property is the percentages that happen in a normal distribution. If you go 1 standard deviation above and below, you would expect 68% of the data to be there. So getting back to our multiple choice question test, which formed a bell curve, we already said that the average was 5. If I gave you that test, I could also find my standard deviation by doing the square root, 20 questions, probability of success was 0.25, probability of failure 0.75, and figure out my standard deviation is around 2. So for that multiple choice question, if 5 is the average, if I go up 2 to 7, down 2 to 3, I would expect 68% of you to get somewhere between 3 and 7 on that test. And that'll be accurate, really accurate. You guess on the whole thing, this happens. I'm going to say 68% of you are going to happen between 3 and 7. If we go 2 standard deviations above and below, adding these numbers up is roughly 95%. So 2 standard deviations below 5, 3, 1, 2 standard deviations above, 1 to 9, I would expect 95% of you to get between 1 and 9. And as soon as you go 3 standard deviations and add up the percentages in them, it's almost 100%, 99.7. There's only 0.3% that would fall outside of that on either side. So because of that, they made up a rule. It's called the 68, 95, 99.7 rule. I like it when the rules really explain what they're... They could have given this a really bad name. I don't know. The numbers are different. Or they call it the statistics rule. Really vague. But the name of this rule, if you can remember the name of the rule, you remember that 68% approximately within 1, 95 within 2, 99.7 within 3. So what we're going to do is we're going to draw normal distributions for data, and sometimes we're going to draw a standard normal distribution. In a standard normal distribution, it's the same bell curve. The mean is in the middle, but we always call the mean 0. And then we count by standard deviations. Up 1 standard deviation, or down 1 standard deviation. This is called the standard normal distribution, where the mean is 0 and the standard deviation is 1. There's a nice fancy Greek letter for this, but you don't have to worry about knowing about that. I believe that's phi. Okay. When you have a standard normal distribution, the scores 1, 2, 3, which count for standard deviations, they have a special name. They're called z-scores. That's it. You already did the first part. Okay. This you don't have to know, But if you wanted to graph a nice bell curve in your graphing calculator, that's the equation you'd have to put in. Looks relatively simple, doesn't it? It's got an E in there. You need to know your standard deviation. You need to know your average, your mean. If you plug that in and type that into your calculator, it will draw you a nice bell curve. The nice thing is our graphing calculator has stuff built in, so it'll draw it nicely for us. We don't have to know its formula. It's also interesting because it's the first, not very often you have functions with 3 variables, eh? So the mean, the median, and the mode are all the same, and everything is symmetrical. Oh, did I not put this page in there? Good. Don't write it down. You can look it up on the video later. All right. Area under a normal curve represents a probability, your chances of something happening. So the fact that the area under one standard deviation to another standard deviation is 0.68, that's because it represents 68%. We have a distribution, normal CDF, on our calculator, which lets us figure out how to calculate that percentage. Very useful. And we'll look at some examples on how that's done. So here are some actual examples of things that are normally distributed. If you measured chest sizes of men, 18-year-old men, there's a mean of 95 centimeters and a standard deviation of 8 centimeters. What is the probability that an 18-year-old male has a chest size between 87 centimeters and 103 centimeters? So what we could do for this, it would draw out a little normal curve. On our normal curve, we label the middle value with the mean. We label 3 standard deviations above and 3 standard deviations below. So since the standard deviation is 8, add 8 3 times, subtract 8 3 times. Then once we have that diagram drawn, what is the probability? It's between 87 and 103. So what we're looking for is that area. Now we have the 68, 95, 99.7 rule. You can probably estimate it pretty well. Can you see it's exactly 1 standard deviation below and 1 standard deviation above? So using the 68, 95, 99.7 rule, we would estimate this to be 68%. Using our calculator, go normal CDF, and just to show you how this shows up on your calculator, so go to distributions, normal CDF is the second one. It says a lower bound. So we were going from 87 to 103. A mean of 95 and a standard deviation of 8. So if you have an older calculator, you have to know the order to type these in. If you have the newer calculator, it tells you what things you wanted. It's kind of nice. For your exam, you will all have a calculator given to you that has the newer version on it. So push enter to 3 sig figs, 68.3%. Oh, I'm going to see if I can remember that. If you go to the distributions and go to draw, shade norm, push enter on that, the lower was 87, upper 103, mean color green. Second stat plot. I'm trying to think if there's a way to set our window up nicely or if we have to do it ourselves. So 87 to 103. Yeah. Window. We want to go from, according to the picture that we've drawn here, 71 to 119. For the X scale, we're going to go by eighths because that's our standard deviation. And let's see if this makes a difference when we graph. No, second, draw, shade norm. And we have to retype things in every time. So can you see why? Oh. Thank you. All right. Well, for the most part, I don't like using shade norm because it takes so long to set it up. And you can get the same value without setting it up. I will figure out how to set it up better and show you later. What's the probability that an 18-year-old male has a chest size less than 87? So now we can take out our shading here, take out our another crayon. Now we're figuring out this part, less than 87. You can use your 68, 95, 99.7 rule to estimate. If the green part here was 68, does it make sense that this part here would be 34? And this half is going to be 50. So 50 plus 34 would make 84%. If we wanted to find the purple part, 100 minus 84% would leave us with about 16%. That's our estimate using the 68, 95, 99.7 rule. So you can use it anytime you have values that hit one of your standard deviations. Now, using your calculator, for normal CDF, notice that I have that negative 1 e to the 99. That is scientific notation for a very, very large negative number. Negative 1 with 99 zeros behind it. That's a pretty big number. Okay? So I'm going to go to distributions. Notice that when you choose normal CDF, you can write in negative 1 e to the 99. Upper bound was 87. We get 15.9. Now you don't have to go, right? Have you ever seen an 18-year-old man with a negative chest size? Like a black hole? Black hole for chest? Probably not. what would what even 0, if you had a chest size of 0, that would be like non-existent. Very unlikely as well. So if I go to my normal CDF and I said, instead of using a huge negative number, if I started with 0, would it make a difference? No. In fact, if you go back 5 standard deviations, which would be from 95, go down 40 to 45, no, 55. Okay. This is part of the understanding part. 5, if I went down to 45, 45 is still highly, highly unlikely. 5 standard deviations away. 3 standard deviations is kind of the limit. Anything beyond that is really unlikely. Notice if I do 5 standard deviations and I paste, the number changes a tiny bit, but where? Not until the 1, 2, 3, 4, 5, 6, 7, the 10th decimal place. So 5 standard deviations as a minimum below, or 5 standard deviations as a maximum above is enough. If you want to have all the probabilities included, you should go as a minimum of -1 e to the 99 and 1 e to the 99 for a maximum. But there's going to be such an unlikely, right? Maybe one day you meet a man with a black hole for a chest. But I think it's pretty unlikely. And so 5 standard deviations for a minimum would be enough, because your answer needs to be to 3 sig figs. And at 5 standard deviation, it only affects the 10th significant figure. What is the probability that an 18-year-old male has a chest size greater than 87? Well, we already estimated that, right? 34 plus 50 for 84%. That's our estimate using the 68, 95, 99.7 rule. It's 84.1, so our estimate was really quite accurate. How do you know if a question is a normal distribution question? Well, often the question says, blah, 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 are normally distributed, blah, 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 blah. So they kind of tell you right in the question, oh, this is a normal distribution question. If it's a normal distribution question, then you can draw your bell curve. Label 3 standard deviations above and 3 standard deviations below. So these are nice big chocolate bars, 232 grams. It's probably about, that big. Right before lunch, that sounds pretty good. When you buy a chocolate bar, it says the weight on there. But would you agree that that can't be exactly right? There's manufacturing problems. Sometimes, like Smarties, sometimes that one box gets an extra Smartie. It's going to weigh more than another box. I remember once, I must have been in about grade 7, huge disappointment. I bought a bag of chips. It was all full of air and puffy. I opened it up and there was 1 chip inside. I got, like, it said 36 grams or 72 grams on the side, but that one got screwed because there was only 1 chip inside. So as a business, you want to have your standard deviation be small because you want people to expect the same thing, right? One of the reasons why a restaurant like McDonald's is popular is because if you go somewhere else, you can expect that it's going to taste the same no matter where you go. They want no big standard deviation. It's not like, oh, the Big Macs in Quebec are terrible, but they're really good in Vancouver. No, they want it to taste the same so much. When I lived in Bolivia, the first ever McDonald's opened up in Bolivia. For Bolivians, it was like a 5-star restaurant. They thought it was like, because it's like this famous restaurant, and they tried to make the restaurant the same look and everything as it would be anywhere else in the world. So, for example, in Bolivia, most of the time you go to a public washroom and it is not very pretty. It's really run down and quite disgusting. But you go to a public restaurant, if you go to McDonald's, they have like, we have to check it every 30 minutes. I had Bolivian friends who said they went into the McDonald's just to see the bathroom because it was so amazing. The other crazy thing is, in order to keep things the same standard, okay, for the French fries, they imported potatoes from Canada, sent them to Bolivia to make the French fries so that they would taste the same as French fries anywhere else at a McDonald's, okay? The potato originated in South America. In fact, Bolivia has the most variations of potato than anywhere else in the world. I had purple potatoes. They had freeze-dried potatoes. They have all crazy different things. But they couldn't use potatoes from Bolivia because then they were afraid it would taste different. And if you were from North America and happened to go to that McDonald's, you would want your French fry to taste the same. Or at least the company thinks you would. So you want your standard deviation to be small. So in this case, 232 grams, standard deviation of 3.6. That means you could get lucky and get one all the way up to 242 grams, 10 extra grams of chocolate, and be jumping off the walls all day, right? But you also don't have to worry about getting less than 222. How many weigh less than 233.9? Well, we could go to our normal CDF on our calculator. You wouldn't have to put the -1e in the 99. 5 standard deviations would be enough. Or you could put 0 in there. You have a 70% chance that your chocolate bar is less than 233.9 grams. All right, I want you to try this next one on your own. Pick your answer. Draw your curves. Get your percentage. So now we're looking at a standard normal distribution. So again, this notation, the first number tells you what your mean is. The second number tells you your variance. So if the variance is 1, square root of 1 would be 1 for your standard deviation as well. And then this is what the notation looks like for probabilities. What's the probability that Z is less than 2.68? So if you draw your distribution, 0, 1, 2, 3, -1, -2, -3, there's 2.68. You could do normal CDF in your calculator, and it tells you roughly 99.6% chance. So with that idea, I'd like you to try B and C. Greater than -1.41. As an estimate, you could say this is 50%, This will be another 34. That's 84. So it's going to be more than 84%. Use that as an estimate. Seems like our answer is right. And check the last one. It says between 0.2 and 1.71. Again, it's just plugging it into your calculator, putting in the right values. You should have got 37.7%. So, another thing that your calculator has is something called the inverse norm. Because sometimes they'll give you questions where they tell you the percentage and ask you to find the score. So let's look at an example and see how to use it. So if they tell you the mean is 60, standard deviation is 7. That's the results on a math test. The average was 60%, standard deviation was 7. What score would separate the top 10% from the class? So if we draw our curve, I'll draw it right here. Here's our bell curve. Okay, we've got 60 in the middle, 1, 2, 3 above, 1, 2, 3 below, 67, 74, 81, 53, 46, 39. We're looking for somewhere here to be 10%. Now, the inverse norm button on your calculator, this 0.9 is because it always calculates from the left. So if I want the top 10% from the left, would it make sense that the other side would be 90%? So where do we find it on our calculator? Again, we go to our calculator, we go to distributions. After normal CDF is inverse norm. The area is 90%. On the new ones, it even lets you, if you wanted to calculate from the right, but on the older calculators, it only goes from the left. 90%, the mean was 60, standard deviation was 7. $68.97 to 3 sig figs rounds to 69.0. So if you scored 69.0 or higher, you're in the top 10% of this class. What about the middle 50%? So now, take this out. Now I'm looking for this to be 50%. If that's 50% and it's symmetrical, would it make sense that that would be 25% there? And so if I wanted to find the bottom score, I do inverse norm of 25%. If I'd want to find the upper score, I do the inverse norm of 75%.